All right. So right off the bat, let's try and do this in the context of things that we've already done. We've already done sine and cosine. We've done a lot of work with sine and cosine. Let's not reinvent the wheel. If we can take what we understand about sine and cosine and apply it to what is going on with our other four, maybe that'll make our lives easier. How can I rewrite tangent of x in terms of sine and cosine? Yeah, this is sine of x over cosine of x. In terms of thinking about features of this function, we had looked at like domain and range for sine and cosine before. I'm a little bit less concerned with that here, but there are some things that I want to highlight. For instance, is the domain going to be quite as flexible as it was with sine or cosine, or do we have some domain issues that we might run into here? Why might we run into some domain issues here, Samir? Because of the way I asked the question? Okay. What about tangent, specifically written as sine of x over cosine of x, points us in the direction of maybe we're going to run into some problems with our domain? Dividing by 0. Okay. So we need to worry about dividing by 0 here if cosine of x is ever equal to 0. Now, when cosine of x is equal to 0, is this going to be a regulated 0 of the denominator? In other words, is there something in the numerator that will balance out the fact that cosine is getting really, really small? Or is this going to be an unregulated 0 of the denominator where cosine being really, really small is going to really dominate the function? It's going to be unregulated. There's nothing in the numerator that's going to cancel out with cosine getting really, 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 really small. And so what are we going to get as we get really, really close to the zeros of my cosine here, to the zeros of my denominator? We're going to get asymptotes. Exactly right. We are going to get vertical asymptotes around the zeros of cosine for tangent. So dividing by 0, because it's an unregulated 0, we get asymptotes. Asymptotes where cosine of x equals 0. Okay. So thinking about our standard rotation around the unit circle, what are the two angles in our like typical rotation for which cosine is 0? When is our x value on the unit circle 0? Okay, what is the angle that goes with this? Yeah, pi over 2 is 1. And 3 pi over 2 is the other. Fantastic. So pi over 2 will have an asymptote. And at 3 pi over 2, we'll have an asymptote. So zeros of cosine give us asymptotes. What are we going to find at the zeros of sine? Because every other value that I have is a 0 of sine rather than a 0 of cosine. What happens to tangent when sine is 0? So we said cosine can't be 0 because it creates asymptotes. What happens when our numerator is 0? What's 0 over anything? 0 over anything other than 0 is going to be 0. And so we end up with a bunch of midline points at the zeros of sine. Yep. So if we're doing what we were doing yesterday, we get like 0 and then asymptote, and then 0 and then asymptote, and then 0 then asymptote, 0 asymptote, 0 asymptote, on and on and on. Pretty hard to play connect the dots when the dots are like being broken up by these asymptotes that we have every so often. We know that we're going to approach the asymptotes. We know we're going to do so with like massively explosive behavior. The next thing then is figuring out what direction we are going to be approaching the asymptotes from. And to do that, we can take a look at our x-axis and think about what quadrant it is referring to when we live where we are currently living. So for instance, if I am between my first 0 here and pi over 2, my first asymptote, what quadrant do we have that sits between 0 and pi over 2? That's the first quadrant. What quadrant do we have that sits between pi over 2 and pi? That's our second quadrant. What quadrant do we have between pi and 3 pi over 2? That's our third quadrant. And go figure, what quadrant do we have between 3 pi over 2 and 2 pi? That's our fourth quadrant. What is true about my x and my y, about my sine and my cosine in the first quadrant? Both are positive. And so a positive number divided by a positive number is going to give us positive numbers. That means that as I get close to this asymptote, I must do so from above. I'm going to move in with going towards positive infinity, essentially. Okay. In quadrant 2, which would be between pi over 2 and pi, what is my xy information going to look like? X is going to be negative, y is going to be positive, and a positive divided by a negative is going to give me a negative. In quadrant 3, what's true about my x and my y? Both are negative, and a negative divided by a negative is going to give me a positive. And then in quadrant 4, what's going to be true about my x and my y? And a negative divided by a positive is going to give me a negative. Okay, tangents, a little bit weird. We like started at kind of an awkward frame. We're like halfway in between some of these. We could continue this. If I go backwards a rotation by pi over 2, that's going to put me in quadrant 4. We go clockwise by pi over 2, that puts me in quadrant 4. And we just said we're negative in quadrant 4. So we're going to be doing this, and we could imagine that we would, continue on if we move to the right as well, so on and so forth. Okay. Let's think about the period for tangent. How long does it take? How far do I have to travel before I start seeing the same image over and over and over and over again? It only takes me pi before I start to see the same thing, right? By the time I've gone all the way around my circle, I've seen the same set of x values, I've seen the same set of y values twice. And so rather than a full rotation being my period, tangent actually has a standard period of just pi. And because of that, we don't have to worry about nearly as many x values when we're actually doing this process if our goal is just to graph a single period of tangent, which has been our goal, right? We're just graphing like one period of the function each time. Now, generally speaking, it'd be kind of weird if we did like 0 to pi. Not saying that it would be like wrong, but kind of picking like a place in our function where we're being like split in half is kind of awkward. And so generally speaking, when we're looking at tangent and secant, actually, sorry, a little bit of a Freudian slip there. When we're looking at tangent and cotangent, we want to make sure that we're going from asymptote to asymptote. We want to start an asymptote. We want to end at an asymptote. Any two could work. Conventionally, though, the two that we care about are going to be starting at, so for our x values that we care about, We're going to start at negative pi over 2. We're going to look at what's going on at 0, and then we're going to look at what's going on at pi over 2, and that takes us to asymptote, midline, asymptote. We don't really have like maxes or mins here. Like, so there's less that we have to worry about. We don't really have to track those y values quite as well. But those are the main three, and then it's just a matter of kind of, it's almost like an x cubed function between those values. Say again. Yeah, good question. So does the notion of amplitude make sense when we're looking at a function like this? Not really, because we define the amplitude as like the distance between our maxes and our midlines and our mins and our midlines. And you'll notice that here, there is no maximum, there is no minimum. We're going towards positive negative infinity. So the amplitude doesn't work as like an idea. Thinking of it as undefined as I think completely fine. But you could also just think like that word just doesn't quite work to describe like what is going on with this function. Like an example off the top of my head, like saying that, you know, it's a very fluffy rain, and we could even draw a meaning from that, but like it doesn't, the descriptor doesn't quite work for like what we're trying to describe, things like that. Okay. So we have no y values that we really care about other than the midline. We have fewer x values that we have to care about, and the pattern is a lot more simple. We just like, it's like an x cubed function. So generally speaking, I think tangent's a little bit easier. We just have to modify a couple of things as we go. So I want to take a look at, let's see here, where's my, taking a look at the 6162 worksheet. I want to take a look at example 3 here. So we are told that f of x is equal to 2 times the tangent of 2 times x minus 3 pi over 4. And we are trying to graph this particular function. We're going to go through our kind of standard litany of questions. Amplitude, period. We want the phase shift. We want the vertical shift. And we want the midline. In this case, what would our amplitude be? Not defined, because it doesn't exist, because amplitude doesn't work. Good job not letting me catch you. This is just not something that we have to worry about, not applicable. With our sine and our cosine, how did we find the period of the function? It was 2 pi over b. Where did that 2 pi come from? That was like the standard period for sine and cosine, which is to say that it takes a full rotation in order to get one distinct image for sine and cosine. For tangent, what's our standard period? Pi instead of 2 pi. And so to find the period here, what should I do? It's going to be pi over b instead of 2 pi over b, the 2 pi being replaced with the pi just because we get a unique image of tangent twice as often. Which in this case is going to be pi over 2. What is our phase shift? Positive 3 pi over 4. Absolutely. What is our vertical shift? None. You could say 0. You could say does not exist. Whatever is fine. And therefore, what is our midline? Just y equals 0. So I do want to note, this too does still like do things. And we could incorporate that into our graph. Particularly, this would tell you what's going on like halfway between midline and asymptote. So this is like the halfway between mid and asymptote. And you'll do that like in the positive direction, and then you do that in the negative direction. So like there's stuff that we can do with that. I don't care for that level of precision, but if you were trying to figure out between like two different tangent functions that like all the x's lined up and it was just between the y's, that 2 there is telling you what the y value should be at the halfway mark, or the negative y value at the opposite, at the negative halfway mark. All right. So let's take a look at then our x's. For our x values here, don't really have to do anything with the y values, but for our x values, we said that negative pi over 2, 0, and pi over 2 are the ones we cared about. And then how did I transform these for sine and cosine? What would my first step be? Say again? Reverse PEMDAS order. What should we do first? But we want to always be doing the opposite. Divide by 2. Divide by b first. That gives me negative pi over 4, 0, and pi over 4. And then what should we do? Let's go ahead and add 3 pi over 4. I get pi over 2, 3 pi over 4, and 4 pi over 4, or pi. Phase shift. So for the graph, so it's going to be pi over 2, 3 pi over 4, and pi. These are asymptotes. And what's our midline in this case? Have we done anything to change our midline? No. And so our function, I'll use our function looks like this. And then that image would like continue on and on to the left and on to the right, but we don't really need to draw that. You can if you want to, but I don't really need you to. Questions with tangent. A little bit easier than sine and cosine. I guess the only thing to remember is that the x values are negative pi over 2, 0 pi over 2, which is a little bit weird that we're starting at negative pi over 2, but that just gets us a nice clean picture. It's also not the only option. You could do pi over 2, pi, and 3 pi over 2, but the math gets not harder, but a little bit more obnoxious when you don't have 0 in the mix. I think so. Yeah. And we could make notes here, like for instance, again, if this is my halfway mark between the two, then this y value should be 2. Like that should be 2. And then if this is my halfway mark, this y value should be -2. Like there's more that we could expand upon there, but that would be like the full image, and that would be like more than perfect. And again, that -2 is coming from the green. Yep. They're generally, so for sine, cosine, secant, cosecant, 0 through 2 pi, just every 90 degrees. It's only going to be different for tangent, and it's only the first half of that for cotangent. So cotangent's not as weird. Tangent's the only weird one that incorporates the -pi/2. Cotangent just does the first half of the others. And that's just because of where the asymptotes end up falling and where the mid values end up falling. Good question. Other questions here? Not too bad? Good. Not eldritch horror levels of mind breaking just yet. I'd say we'll get there, but really today is kind of coasting. If you felt good about yesterday, then today is not going to be bad. Let's go ahead and do the same thing for cotangent. I'm not gonna get like we're not gonna go over a cotangent example. It's the same thing as tangent. It's just like different x values because what your asymptotes are and what your zeros are going to be different. What is cotangent in terms of sine and cosine? Cosine over sine? And so before we had our asymptotes when cosine was 0, and we had our zeros when sine was 0. And what has happened now? They switch. So everywhere there was a 0, there's now going to be an asymptote. Everywhere there was an asymptote, there's now going to be a 0. I get asymptotes at 0. I get asymptotes at pi. I get asymptotes at 2 pi. So Jake, this is what I was kind of saying when like the framing works a little bit better because we don't start like in the middle of an asymptote. We like actually 0 to pi is asymptote to asymptote. So that's a little bit more convenient for cotangent. And then we said these are going to be zeros here. Zeros, zeros, zeros. The other weird thing about cotangent is because the first quadrant that we start in is quadrant 1 rather than quadrant 4. We don't start negative and positive. We start positive and negative, right? So with -pi/2 to pi/2, we go quadrant 4 to quadrant 1. With 0 to pi, we're going quadrant 1 to quadrant 2. And so we essentially are flipping what is going to be positive, like when we're going to be positive, when we're going to be negative. We're not actually flipping it. It's just like the direction is going to look a little bit funny. And so we are positive in quadrant 1, negative in quadrant 2, positive in quadrant 3, negative in quadrant 4. That's not me doing anything. That's not like a transformation or anything. That is just like the consequence of where the zeros are relative to the asymptotes and what quadrant that corresponds to, right? So before it was starting negative in quadrant 4, ending positive in quadrant 1. Now it's starting positive in quadrant 1, ending negative in quadrant 2. Which essentially flips us upside down. But otherwise, that's it. Questions with cotangent? Yep, that's it. Well, same period and everything. I'll mention here. What would make sense if we're trying to go asymptote to asymptote for our relevant x values? What would easy ones be? Yeah, I like 0 pi over 2m pi. That would go asymptote, midline asymptote. Yeah, zeros and asymptotes relative to tangent have just switched. And then because of the framing, we start positive and negative versus start negative, ending positive. But that's just like, that's like, it's not a math thing. That's just like the way things oriented relative to where everything else is. So. Which I guess is a math thing, but it's not like a computation thing. Tangent, cotangent, not too bad. Maybe a little easier even than sine, cosine. No, not at all. Oh, man. Okay. Okay. Then let's continue on. We're going to do the exact same thing that we just did now with cosecant. And we'll do secant as well. Cosecant is related to which of the trig functions that we already know? This is sine, so this is like 1 over sine. And in kind of a very similar fashion to what we saw with tangent and what we saw with cotangent, what does it mean now that I have a sine in my denominator rather than having a sine in my numerator? So our sine function, let me go ahead and graph that in really quick. So 1, -1, it was mid, max, mid, min, mid. Something like this. That's pretty good. It's okay. What is going to happen when I am taking the reciprocal of this particular function? So what's going to happen to my zeros? What are they going to turn into? What happens now when my sine function is 0? What happens when my denominator is 0? What do we get? Undefined, which creates what kind of behavior? Is this going to be a regulated 0 or an unregulated 0? Unregulated. There's nothing in the numerator. What did that create just now? It creates asymptotes. Okay, so everywhere where we have a 0 for our sine function, we are going to get an asymptote for our cosecant function. So asymptotes in this case, 0, pi, and 2 pi. Up here is where my sine function was at its biggest, it's at its maximum. If I'm making my denominator the biggest it's going to be, what does that create? If I take my denominator and make it as big as possible, what do I get? What happens to my number? Say again. When I divide by a bigger number, do I get a bigger answer? No, I get a smaller number, right? I get a minimum value when my denominator is at its largest. This maximum flips upside down and becomes a minimum. Likewise, what happens when I take my denominator and make it as small as possible? I get a larger number. My minimum flips upside down and becomes a maximum. And that is not only it, that is our strategy for how we are going to graph this. We're going to graph the sine function. We'll do a dashed line for it just to make sure we know it's not part of our graph. And then everywhere we have a 0 or a midline point, that's going to become an asymptote. And then everywhere we have a minimum, we're going to flip it upside down and it's going to become maximum. Everywhere we had everywhere we had a maximum flips upside down becomes a minimum. Everywhere we had a minimum flips upside down becomes a maximum. Take it? Yeah, just connected now. Well, they couldn't be connected through the asymptote, right? Yeah, yeah. Same thing for cosecant, or sorry, we just did cosecant. Same thing for secant. What is secant in terms of trig functions that we already know? That's 1. Yeah, that's going to be 1 over cosine here. My just it's great. All right. Sorry about this. Oh. Go transition to being a little more old school. Okay, so we said for our secant function here, which was 1 over cosine pi over 2 pi 3 pi over 2 and 2 pi 1 and -1. For our cosine function itself, we said we go max, then mid, then min, then mid, then max. So looking at something like this. Ambitious. And since we are instead looking at 1 over cosine of x, what is going to happen to my zeros? They're going to become asymptotes. So I get asymptotes at pi over 2 and 3 pi over 2. And what's going to happen to my, let's do the minimum first. What's going to happen to my minimum here? Yeah, it flips upside down and becomes a maximum. And then what happens to my 2 maxima up here? They flip upside down and become minima. Again, camera angles are kind of awkward here, just because like we're not going asymptote to asymptote to asymptote. Like with cosecant, you could imagine that this would continue off until it hit an asymptote. You could imagine that this would also continue until it hit an asymptote. But like that would be the standard like frame that I would draw. If you wanted to shift it over, if you wanted to go -pi to 3 pi over 2 just to get a cleaner picture, you certainly could. I do not need you. Yes. Another question here. Any questions here with secant and hopefully like exactly the same thing as sine and cosine, except there's like one little extra step at the very end, which is just zeros become asymptotes, flips upside down. That is exactly how we're going to treat these. Yes. We are literally going to graph the sine or the cosine graph, and then we're just going to do this to it. Yeah. Yeah. It is not only a good like way to get there, it's just actually what we're doing. It's just like the. In terms of like amplitude here, the word amplitude probably loses meaning when we're considering something like this, because like amplitude really is supposed to be talking about like waves. It still kind of preserves its meaning. Like this distance is still the amplitude or equivalent to what the amplitude is. That distance is still the amplitude. And so technically, if we're looking at like local mins and local maxes, then the amplitude idea does still work. It's just it no longer works with like the absolute min and the absolute max, because there is no longer an absolute min or an absolute max. Yeah, if you told me that the amplitude of this would one, I'd probably give you credit, even though I'd raise my eyebrows a little bit. Probably stretching the definition a little bit, but certainly when we're talking about the corresponding cosine graph or the corresponding sine graph, that amplitude is giving us something very useful for what we're going to do with this graph. Still telling us how far away our curve is from the middle at its slight. All right, should we take a look at an example? Sure, let's do number 14 on that worksheet there. That one's kind of got everything going for it, so a good example to showcase. Okay, so 14. This is going to be 2 times the secant of x, 2 times the secant of 8/3 times x minus what, 3 pi over 4? Is that right? No, pi over 4. No, not pi. I'm just like entirely losing my mind. Plus pi. And then plus 1. Okay. In order to better understand this function, what is the sine or cosine function that is going to be very closely affiliated with our secant function? Yeah, exact same thing, except instead of secant, let's look at what's going on with cosine. Now we're just doing a problem like what you might expect to see. I don't know if we had like a quiz tomorrow. Crazy. The blue is fair game for tomorrow's quiz. The red is not fair game for tomorrow's quiz. The blue is fair game. I will probably pick numbers that are nicer than 8/3. So. Well, we're going to deal with the cosine first, and then at the very end, we're going to adjust it. Oh, so. Yeah. Yeah. So these aren't equivalent. They're not the same thing. But we're going to squint our eyes really, really aggressively and pretend that for now that this is actually there. Yeah. I didn't bring my glasses today, so this looks a whole lot like cosine. Yeah, so like the U that's like the old Unit 6. I'm calling it 4G, like the graphing. Yeah, but sine goes. Okay, let's go through our list. Let's go through our typical stuff. We can talk about, certainly here, we could talk about the amplitude of the cosine function. We talk about the period. We could talk about the phase shifts. We could talk about the vertical shift. We could talk about the midline. Well, what is our amplitude here? 2. How am I going to find my period? Yeah, 2 pi over b, which in this case I'm going to write as 2 pi times 3 over 8, which gives me 3 pi over 4. Yeah. We're working with the cosine function. We're squinting our eyes. What is our phase shift going to be? Negative pi. What is our vertical shift going to be? 1. And then therefore, what is our midline going to be? Y equals 1. Very nice. Let's do the easy ones first. Let's do the y values first. So -1, 0, and 1 for min, mid, max. What do I do first? We didn't see a great example of this yesterday, but I kept making us write it in even though it wasn't doing anything. If we're just following PEMDAS, doing the thing that we expect to happen to our y value, what happens to our y value first? Transformation. We're first going to multiply by 2. -2, 0, and 2. And then what's going to happen to our y value? Then we're going to add 1. That's going to be -1, 1, and 3. Right, that's adjusting our y value by multiple. So we multiply by 2 to adjust our y value. And then adding 1, step this one. Our R. Okay about the y's? Understand? We're just doing PEMDAS order. We're just doing the thing that we want to do. We're doing the multiplication first, then we do the addition. It's the x's that are kind of tricky because we have to do the opposite of everything that we're trying to expect to do. So for instance, we have to do the opposite of PEMDAS order. We have to undo everything that is being done here. What are our starting like 5 significant values of x? Nice. According to PEMDAS, what is the first thing that's going to happen to our x value when we plug it in? Parentheses first. The first thing is going to be the plus pi. Then it's going to be the times 8 pi over 3. We're going to invert that whole process. We're first going to undo the 8 pi over 3, because that happens last. And then we're going to undo the plus pi, because that happens first. What is my first transform on this going to look like? What would you could multiply by something. I would divide first, but then we'll do multiplication when we're doing the division. We want to do the opposite of everything that we see in the function. Divide by 8 pi or 8 over 3. because the y values are just like consequential, like that just matters. I run my machine, and then after I run my machine, it gets doubled, and then it gets added to one, so you double it. Here, we don't love the fact that they're messing with our x values. If we just tried to plug in 2 pi there, it's not going to end up where we want it to be. And so we have to take countermeasures. This is messing up our inputs. We have to fix our inputs on the front end so that when they get processed, they're where we actually want them to be. So we know eventually our input is going to be multiplied by 8/3. So we take our inputs that we want, we divide them by 8/3 so that when this hits, it cancels this. I'm going to multiply by 3/8 here. I get 0. I get some fun numbers, 3 pi over 16. I get 3 pi over 8. I get 9 pi over 16. Very good. And I get 3 pi over 4. By 0. Okay. What then am I going to do? It's my second X transformation that I want to apply here. Yeah, we're going to undo the plus pi here. So we'll subtract pi from everything. 0 minus pi is a nice one. That's just going to be negative pi. 3 pi over 4 minus pi. For this, it's convenient to have your pi have a matching denominator. So I'm thinking like 16 pi over 16. I'm thinking 8 pi over 8. I'm thinking 4 pi over 4. So 3 pi over 16 minus 16 pi over 16 gives me a negative 13 pi over 16. 3 pi over 8 minus 8 pi over 8 gives me a negative 5 pi over 8. 9 minus 16 gives me a negative 7 pi over 16. And then 3 minus 4 gives me a negative pi over 4. Which would suck if I hadn't said, hey, you get to pick X values on your axis that are convenient for you. So pick those 5 X values on your X axis as being ones that are convenient for you. Like if you label your X axis as this, and then you just put your points there and know that they're evenly spaced, they're 3/16 apart, 3/16 of pi apart, then like you're good. Questions with the work on the front end before well, actually we have one more thing to do. But questions with this work, with the transformation work. Well, no, these are the ones that we want to be actually plugged into the function, but these are what they have transformed to be. So these are the correct X values. These are what they were originally, but these are the transform. You need the transform, otherwise you're not graphing. Like try plugging in 2 pi into that equation and you're going to get something completely different. Actually, I think 2 pi is a bad example. I think 2 pi works out nicely. It's also 0. Any other of these, though, would not work out. Yeah, I guess that makes sense because let's then, before we graph, we have one more thing to talk about. Because my function is cosine, what's the pattern that these are going to follow? Max, mid, man, mid, max. Okay. So let's see here. Again, I'm going to be lazy. I'm going to pick values of x that are convenient for me. They are equally spaced, so there are like ways that you could get around having to do this, particularly if you know negative pi, if you know the negative pi over 4. All right, so we know negative pi, no, negative pi over 4. Perfectly between the two is going to be negative 5 pi over 8. Between these two, negative 13 pi over 16. Between these two, negative 7 pi over 16. Then our y values that we cared about, we said our max is going to occur at 3. We said our min is going to occur at negative 1. And we said we have a midline at y equals 1. Max, mid, min, mid, max. I'm going to connect these with a dotted line just because we don't actually care about the cosine function, just using it. Get what we actually want. Something like that. We done? We done the thing? No. If this were the quiz, that'd be great. That'd be perfect. Full credit. Awesome. Very well done. Nice one, break. But if this were, I don't know, say like a test that we had or something the week after we got back to this, right? And I'm asking you for secant, what's going to happen to my midline points? They become asymptotes. My mins and my maxes flip upside down. Yeah. They're the midline points becoming the asymptote. Because the midline points are where the cosine bit is 0. It's just not always on 0 because I am then sometimes taking that 0 and adding something to it. But in this case, it's that thing becoming 0 that's creating the asymptote. Yeah, so importantly, it's not the zeros of my function that become asymptotes. It's the values on the midline that become asymptotes. Because that's when the cosines become 0. And if you really wanted to, you could continue this off just to make it a cleaner picture, but you do not. Questions with cosecant and secant?
The midline from your host, you can't become the asymptotes.
Yeah. Yeah. Yeah, so on sine, our pattern is mid, max, mid, and mid, which becomes asymptote, min, asymptote, max, asymptote. Good question. Other questions? Not too much worse than sine and cosine, hopefully. Hopefully, like exactly the same thing. There's just like one step at the very end to remember to do. Just all right. We've got about a lot of time, right? Yeah, I got about like 25 minutes left. Quiz tomorrow. Final thing we're doing. It's not going to go on this quarter, but it'll go on next quarter. There's the 4445 classwork for that quiz, as well as additional practice in this packet, which while not due tomorrow, will be due when we get back from break at some point, probably prior to the test. So I'm giving you guys the rest of the time to work on that. Yes, and I've adjusted it so that it's reflecting now. Yeah. I think it was set to, it closed last night, but I've adjusted it. Yes.